Usually when you look at a map, there is this overwhelming expectation of absolute authority. You pull up a digital map on your phone, see that little blue dot, notice the crisp lines of the streets and the defined borders of a property line, and you just trust it. It feels completely objective.
Oh, absolutely. It presents itself as a flawless reflection of reality. I mean, humans are basically uh, biologically wired to trust hard visual boundaries. When we see a definitive line on a screen, we just assume a definitive physical equivalent exists in the real world.
Right, but then you step behind the curtain into the actual practice of geographic information systems, and you realize that beautiful, perfect map is essentially, well, a giant mosaic of compromises. It's instrument limitations and, potential errors.
It is anything but perfect. If you put garbage data into a GIS, you get, beautifully rendered, highly convincing garbage out.
Yeah, exactly. Inaccurate data leads to flawed real-world decisions, like advising a client they own a strip of land that actually legally belongs to their neighbor. High-quality data, on the other hand, ensures reliable outcomes. And that is exactly why we are doing this deep dive today.
Navigating those diagnostic muddy waters is what separates someone who just uses a map from a true spatial professional.
Yep, so whether you are deep in the trenches, prepping for the GISP exam, or just aiming to sharpen your, professional geospatial skills, our mission today is to conquer Section 203, which is understanding data quality.
To understand how errors and uncertainties arise in spatial data, and more importantly, how we manage them, we really have to look at the anatomy of the data itself. We're going to be pulling from ISO frameworks, practical quality control tables, and those error statistics you definitely need to master.
Okay, let's unpack this. Let's start with how we even judge if spatial data is viable. I mean, you don't just run a spell check and call it a day. Data quality is it's a multifaceted evaluation.
It really is. It's not just a single grade. We have to look at the core dimensions of spatial data as defined by the International Standards Organization.
So what is the first one we need to know?
Well, the first dimension most people focus on is positional accuracy, which is also known as geometric accuracy. This basically measures the literal closeness of spatial coordinates in your data set to their true locations on Earth.
Right, so if you are mapping a buried fiber optic cable, positional accuracy dictates whether your digital line is within 2 centimeters of the actual trench, or if it's off by 5 meters.
Exactly. And 5 meters off means someone with a backhoe is going to have a very bad afternoon.
Yeah, but physical location is only one piece of the puzzle, right?
Oh, for sure. You could have a polygon perfectly mapped to the exact millimeter of a city park, but if the attribute table labels that polygon as a toxic waste dump, well, you have a massive data quality problem.
Which brings us to thematic accuracy, or attribute accuracy.
Yes. This measures the correctness of the non-spatial data attached to the geometry. Are the city names spelled correctly? Are the zoning codes actually accurate?
So positional accuracy gets you to the correct geographic footprint, but thematic accuracy ensures you actually know what exists inside that footprint.
You nailed it.
Yeah.
Then there is completeness. If you are mapping all the public schools in a county to generate bus routes, and your data set is missing a newly built elementary school, your routing analysis is fundamentally broken from the start.
That makes sense. And closely tied to that would be temporal accuracy or timeliness, right?
Yes, time is a crucial and often overlooked dimension. A data set of those same schools might be 100% complete and positionally accurate as of 2015, but if it doesn't reflect the changes made over the last decade, it's totally useless for current operations.
Okay, so we have positional, thematic, completeness, and temporal. What's next?
Well, perhaps the most technically demanding dimension for GIS analysts, and a major focus for certification exams, is logical consistency. This is the adherence to rules of data structure, relationships, and topology.
I always think of logical consistency like the engineering behind a city's plumbing system.
Oh, I like that. How so?
Let's say you are building a digital model of a water network. You can have all the physical pipes mapped in their exact right geographic locations, which gives you perfect positional accuracy.
Right, the coordinates are spot on.
But if the digital model doesn't mathematically connect those pipe segments at the junctions, like if there are microscopic digital gaps between the lines in your data set, the system isn't logically consistent.
It's just a bunch of disconnected lines.
Exactly. So if you try to run a flow analysis to see how water travels through that network, the digital water will just spill out everywhere at those broken junctions. The analysis completely fails, even though the map looks visually perfect on the screen.
That is a perfect analogy. Topological rules are what make spatial analysis mathematically possible. Setting rules in a geodatabase that state, say, road segments must not overlap or parcel polygons must not have gaps forces the software to maintain logical consistency.
So the data has to follow the rules of its own universe.
Precisely. And wrapping all of these dimensions together is another vital concept, which is lineage or provenance. Lineage is the metadata documenting the source, the history, and the transformations of the data.
Ah, so it tells you if a county boundary was surveyed by a professional team last week using survey-grade GPS, or if it was just digitized by hand from a coffee-stained paper map back in 1998.
Exactly. And what's fascinating here is how all these individual dimensions, positional, thematic, temporal, logical consistency, and lineage, they collectively determine a dataset's fitness for use.
Fitness for use. That sounds like the ultimate test.
It really is. It acknowledges that no data is perfect, and instead it asks, regardless of its known flaws, does this data fulfill the specific stated needs of this particular project?
So context dictates quality.
Very much so. A data set that is perfectly fit for a statewide climate model might be disastrously unfit for guiding an autonomous tractor.
Right. And since we have to measure the real world to build these data sets, we inevitably run into the tension between accuracy and precision. I feel like for anyone studying these concepts, distinguishing the mechanics of those two terms is absolutely critical.
Oh, they are entirely different operational concepts in geospatial science. Accuracy, as we touched on, is how close your mapped values are to the true, real-world values. It's a measure of systematic bias.
So if your instrument is poorly calibrated and constantly shifting every recorded 0.3 meters to the north, your data is inaccurate.
Yes, exactly. Precision, on the other hand, is about the level of exactness and the consistency of the measurements relative to each other.
Let's use that hyperspecific numbers example from the source material to illustrate the mechanics of this in a database.
Go for it.
So if you record a measurement as 123,123.456, the precision of that number is 9, because there are 9 total digits. But the scale is 6, because there are 6 spaces after the decimal point.
That distinction impacts how data is actually stored and processed. You can record a coordinate with a precision of 9 decimal places, meaning your database is claiming to know the location down to the millimeter.
Wow, okay.
But if that point was captured with a cheap consumer smartphone, that highly precise coordinate is entirely inaccurate.
It's precisely wrong. The database has exactness, but the real-world location is fundamentally incorrect.
Exactly. And when we apply these concepts to remotely sensed data, like satellite imagery or drone capture, accuracy actually fractures into 4 distinct technical categories.
Right, because remote sensing is an entirely different operational environment. So what are the 4 categories?
First is spatial accuracy, which is basically the geographic resolution. How much real-world area does one single pixel represent? Second is spectral accuracy, which refers to how well the sensor records specific bands of the electromagnetic spectrum.
Like a sensor specifically tuned to capture near-infrared light to measure vegetation health, because healthy plants reflect infrared light differently than stressed plants.
Spot on. Third is temporal accuracy, which is the specific time and return interval of the satellite. But the fourth, radiometric accuracy, is often where analyses really succeed or fail.
Okay, radiometric accuracy. Explain how that actually changes the outcome of an analysis. Why does radiometric resolution matter on a practical level?
Well, radiometric resolution is the sensor's sensitivity to slight differences in energy. It dictates the number of distinct values that can be recorded for a single measurement. Think about 8-bit data versus 16-bit data.
Okay, I'm with you.
An 8-bit sensor can distinguish 256 different shades of gray. A 16-bit sensor can distinguish over 65,000 distinct values.
That is a massive difference.
It is. So if you are trying to write an algorithm to automatically detect the boundary between a slightly damp wetland and a dry forest, the temperature and reflectance differences might be incredibly subtle.
Oh, I see where this is going.
Yeah, an 8-bit sensor might record both areas as a value of 42, making them completely indistinguishable. But a 16-bit sensor will capture that subtle variance, allowing your algorithm to accurately separate the two environments.
So what does this all mean for you in the field? Because even with 16-bit data and millimeter precision, we face an unavoidable mathematical problem, which is spatial transformations.
Ah, yes, projections.
Right. We live on a lumpy, three-dimensional globe, and we constantly flatten it out onto 2D screens or paper maps through projections and datums. That flattening process basically guarantees distortion.
It's unavoidable.
You can preserve area, or shape, or distance, or direction, but never all of them at once. So, since distortion is a mathematical certainty, doesn't that mean all GIS data is inherently a little inaccurate? How do we accept that?
Well, they are inaccurate, which brings us right back to fitness for use. We manage that inherent inaccuracy by choosing the mathematical projection that minimizes the specific type of distortion that would ruin our project.
Okay, so you just pick your poison.
Exactly. If you are calculating the total acreage of a massive national park, you use an equal area projection. The shapes of the boundaries will look heavily distorted, but the mathematical area will be highly accurate.
But if you're navigating a ship, you'd use a conformal projection to preserve accurate angles and directions, accepting that landmass sizes will be wildly distorted.
Exactly. Since projection distortion guarantees that our data will never be 100% perfect, and, human error is always a factor, organizations have to build institutional safety nets to catch and mitigate those errors.
And that brings us to the operational side of data quality, the battlefield of quality assurance versus quality control.
Distinguishing between QA and QC is a classic stumbling block on the exam. They are two halves of a quality management system, but they operate at totally different stages of the data lifecycle.
Let's break them down.
Quality assurance, or QA, is process-oriented. It is a proactive, managerial framework. QA focuses on defect prevention before data collection even begins.
So instead of the old recipe and cooking analogy, QA is more like setting up a high-tech automated factory. QA is writing a flawless recipe and organizing the kitchen staff so no one bumps into each other.
Wait, I thought you said instead of the kitchen analogy.
Yeah, well, I guess let's stick with the kitchen. QA is the prep work. It's making sure the recipe is perfect and the cooks know exactly where to stand.
I love that. And that maps perfectly to GIS. In spatial data, QA means building a geodatabase with predefined domains and subtypes. By forcing field workers to choose from a drop-down menu of approved tree species, QA physically prevents them from typing oak with a 0 instead of an O.
Oh, that's brilliant. It prevents the error from ever entering the system.
Exactly. Now, quality control, or QC, is product-oriented. It is a reactive corrective tool. QC focuses on defect identification and correction after the data has been collected.
So back to the kitchen. QC is tasting the soup right before it goes out to the customer and realizing it needs way more salt.
Spot on. In GIS, QC includes data validation, which is comparing your collected data set against a known high-accuracy baseline, like checking digitized property lines against legal survey coordinate.
Right.
And it also involves data cleaning, which is the operational work of removing errors, eliminating duplicate records, and running automated Python scripts to flag empty attribute fields.
If we connect this to the bigger picture, maintaining a transparent log of those QA and QC processes is what guarantees the reproducibility of the entire spatial analysis.
Absolutely. If an analyst can't prove exactly how a data set was cleaned and validated, their final conclusions will never hold up to scientific or legal scrutiny.
But let's look at the reality of that QC process. If you have a LiDAR data set with 3 billion elevation points covering an entire state, nobody is checking those points one by one. You have to use sampling and statistics to measure the error of the whole dataset based on a small subset.
Right. You rely on statistical sampling to estimate the overall quality. And there are 5 core sampling architectures you really must be familiar with. Let's frame this around a real-world scenario.
Okay, hit me.
Imagine your team is tasked with verifying the soil contamination across a massive, diverse county that includes dense urban centers, agricultural fields, and protected forests.
Okay, that is a massive logistical challenge. My first instinct would be systematic sampling. Just drop a grid over the entire county and take a soil sample exactly every 1 kilometer. It ensures equal, uniform coverage.
Systematic sampling does guarantee equal coverage, which makes it highly useful in homogeneous areas. But the sources highlight a massive trap here.
Here's where it gets really interesting. If systematic sampling can guarantee uniform coverage, why wouldn't you just always use it?
Because if that 1 kilometer systematic grid accidentally matches a hidden repeating pattern in the landscape, like historical irrigation canals that were also built exactly 1 kilometer apart, you completely ruin the data by introducing systematic bias.
Oh, wow. You might only sample the clean canals and completely miss the contaminated fields in between them.
Exactly.
If systematic bias is that severe of a risk, I'd throw out the grid and use random sampling. The computer randomly generates the sample points across the county, completely eliminating the chance of syncing up with a hidden landscape pattern.
It definitely solves the bias problem, but random sampling introduces a severe logistical and analytical problem. If a computer randomly scatters points, you might get a dense cluster of points in a totally uniform cornfield and 0 points in a highly complex, heavily industrialized urban zone where you desperately need data.
Plus, setting field crews to completely random isolated points across a massive county just destroys your travel budget.
It really does.
So we need a method that respects the travel budget but still generates reliable statistics.
That leads to cluster sampling. You randomly choose a few broader geographic locations, say 5 specific townships within the county, and then heavily sample within those specific clusters.
Okay, so it massively reduces travel time and costs for field crews while still maintaining statistical validity.
Yes.
But cluster sampling still runs the risk of entirely missing specific features. What if none of the randomly selected townships contain the protected forests? We still need data on those forests.
To guarantee representation of all features, you use stratified sampling. You partition the total population into distinct subgroups, or strata, basically separating the county into urban, agriculture, and forest zones.
Ah, I see.
You then take proportional samples from each specific zone. This mathematically guarantees that no single land use type is over or underrepresented in the final error assessment.
That definitely seems like the most robust approach for a diverse landscape. But what about adaptive sampling? Where does that fit into the workflow?
Adaptive sampling is highly dynamic. It involves increasing the sampling density in areas where the features are highly variable or complex, while using fewer samples in large homogeneous areas.
So as the field crews detect higher contamination in an urban zone, the sampling strategy dynamically adapts to pull more data from that specific hotspot.
Exactly. It's incredibly efficient.
So once the sampling is complete, we enter the math of mistakes. We have to calculate the actual error rate of the dataset.
Well,
Let's break down RMSE versus MAE, because the mechanics of how these two formulas process outliers is a guaranteed test topic.
without a doubt, root mean squared error, or RMSE, is the industry standard. Mechanically, it is the square root of the average of squared errors. It tells you the standard deviation of the differences between your predicted values and the observed values.
Right.
But the defining characteristic of RMSE is how it handles large mistakes. Because the formula squares the errors before averaging them, it is highly sensitive to outliers.
Right, so if a GPS unit is off by 2 meters, squaring it makes it 4. But if the unit glitches and is off by 10 meters, squaring it inflates the penalty to 100.
Exactly. RMSE actively punishes massive outliers, drastically inflating your overall error score.
Which is why analysts also rely on MAE, right, the mean absolute error.
Yes. MAE is simply the average of the absolute differences between the prediction and the actual value. Because it does not square the distances, it treats a 10-meter error exactly as it treats 5 2-meter errors.
So it's notably less sensitive to outliers, providing a smoother look at the baseline error trend without being hijacked by one rogue data point.
That distinction is crucial. RMSE punishes the outliers, while MAE ignores the drama and just averages it out.
But what happens when we aren't measuring distances? What if we are running an image classification? Let's say we program an algorithm to look at satellite imagery and identify all the pixels that represent water and all the pixels that represent forest. How do we calculate the error of a categorical classification?
For categorical data, we use a confusion matrix, which is sometimes called an error matrix. You basically plot your algorithm's classification results on one axis and the actual verified ground truth on the other axis. Where they correctly intersect on the diagonal of the matrix, that represents a successful classification. Where they miss, for example, the algorithm incorrectly classified a dark asphalt parking lot as water, the error shows up outside the diagonal.
So it maps out exactly where the algorithm is getting confused. But the sources emphasize calculating the kappa index of agreement from this matrix, rather than just relying on a simple overall accuracy percentage. Why is a basic percentage flawed?
Because a basic percentage can be completely manipulated by random chance. Imagine a map that is 90% ocean and 10% islands. If your algorithm is terrible, but it just guesses water for every single pixel, the overall accuracy will still report as 90% because it got the massive ocean correct.
Even though it completely failed to identify a single island.
Exactly. The kappa index corrects for this. It evaluates the agreement between the classification and the ground truth, and then mathematically subtracts the amount of agreement that could be expected by random chance alone.
That is so smart.
Yeah, a kappa score ranges from 0 to 1. where 1 indicates perfect agreement. A high CAPA score proves your algorithm is actually identifying patterns, not just getting lucky by guessing the dominant land cover.
Man, as we synthesize everything in Section 203, data quality isn't just an abstract academic exercise. It is a continuous, rigorous pipeline of validation. It requires balancing positional precision with thematic accuracy, applying stringent QA rules in the geodatabase, running reactive QC topological checks, and understanding the statistical nuances between RMSE and the kappa index.
And returning to the stakes of this profession, if an analyst fails to grasp these concepts, the real-world consequences are severe. A beautifully rendered map with unverified lineage and poor topological consistency can lead to multi-million-dollar infrastructure projects being routed through legally protected wetlands.
Or municipal tax assessments being completely invalidated in court, like when a GIS measurement doesn't line up with the legal area on a physical property deed.
Really is. This raises an important question, however, about the ultimate nature of the spatial data we spend so much time perfecting.
Oh, where does this lead us?
Well, the sources touch on the concepts of uncertainty and timeliness. Consider the reality of a perfect data set. You apply flawless QA, rigorous QC, your RMSE is incredibly low, and your kappa index is nearly perfect.
Sounds like a dream.
The very second that pristine data set is published, it immediately begins to decay.
Because the physical world refuses to stand still. Rivers erode their banks, new subdivisions are paved, tectonic plates literally shift our coordinate systems.
Every data set, no matter how rigorously validated, is inherently just a snapshot of the past.
Wow, so what does this all mean for the future of the profession? I really want to leave you with this to ponder as you continue your exam prep or head back to the office today. In an era of rapidly accelerating global change, where coastlines are shifting and urban footprints are expanding overnight, at what exact point does a highly accurate map stop being a reliable navigational tool and start becoming a beautifully precise historical artifact? Keep analyzing, keep questioning the data, and good luck on that exam.